So what we're going to look at this evening is, well, it's the number of things involving roots. One of the things that we encounter while we're factoring these polynomials is, well, sometimes they're tricky to factor. And if we can maybe get one factor figured out, well, what's remaining of that polynomial, maybe it's not so bad. So for example, let's say we have this. Let's just suppose x minus c is a factor of p of x. So what this means is p of x breaks down into a product of x minus c times something else, q of x. And we're not sure what q of x could be, but maybe it's something we can also factor. Say it's like a quadratic, and we could use a quadratic formula. So let's say we have something like this. It turns out that x minus 3 is a factor of x cubed plus 2x squared minus 9x minus 18. Now, say this is in fact the case. So what that means is x cubed plus 2x squared minus 9x minus 18, well, it's equal to x minus 3 times some q of x. Now, let's try to find out what q of x is. Now, the way we can do that, if we divide both sides by x minus 3, we'll get that. So this will give us our q of x. So to divide this really quickly, let's use synthetic division. And this is one of the powers of synthetic division. We do have a procedure for doing long division. I mean, that's certainly correct. But as you saw, long division can take a long time. Synthetic division is really fast, and it's great when we have a factor. If we have a factor of some polynomial, we can use synthetic division to divide to get q of x really quickly. So let's see, this is going to become 3. And again, if there's a minus in front of the 3, it's just, that's what we start out synthetic division with. If this is a plus, we would start this out with a minus. Now the coefficients, we don't change those. Those stay the same. So bring down the 1. 3 times 1 is 3. Add these, we get 5. 3 times 5 is 15. Add these, we get 6. 3 times 6 is 18. And add negative 18 and 18, we get 0. And don't forget, for synthetic division, we're adding. So the way it works, this is the remainder, the constant term, or this is the coefficient for x, and the coefficient for x squared. So when we divide this by this, what we get, x squared plus x plus 6. And that's our q of x. So what this is basically saying, x cubed square there, plus 2x squared, minus 9x, minus 18, well, this is going to be x minus 3 times, and then we found q of x, x squared plus x, oh, sorry, 5x. Don't want to forget that's a 5x. That's the coefficient for the x term. 5x plus 6. And that's our q of x. And again, I forgot to write, this is the coefficient for the x squared, coefficient for x, constant term. I forgot to put that number in there. All right. So, okay, that's pretty good. We know what q of x is. Can we factor this out? And we can. It'll break down using the guess and check method. So just to review the guess and check, we need two numbers, a and b, that add up to the coefficient of x. In this case, it's 5, and multiply to the constant term, 6. And what two numbers? Well, 2 and 3. So that says that x squared plus 5x plus 6 going to be x plus 2 and x plus 3. And we can check this. Sure enough, 2 plus 3 does give you 5. 2 times 3 does give you 6. So now what we know is this. This will break down to x cubed plus 2x squared minus 9x minus 18, x minus 3, x plus 2, x plus 3. So all this was really possible because we knew that x minus 3 was a factor of this. So how do we figure out that first critical factor? Because that was kind of the whole trick here. Because this we just used our guess and check to figure out. But we were given this from the beginning, and we just used synthetic division to get this piece here ultimately with a little help of guess and check factoring. So how do we get that first factor? How could we do that without someone just giving it to us? Well, that's where we get into this rational zeros theorem. So the rational zeros theorem works like this. Well, let's think back to that basic form of the polynomial. So again, here we have these bunch of things going on here. We have real numbers, 1. Real numbers. And these could be anything. They could be fractions, they could be irrational numbers, they could be rational numbers, they could just be integers. But there's some kind of real number. We've got our x's. And then in here, n is going to be a whole number. Whole numbers are like 1, 2, 3, 4, 5, 6, 7. This would be some whole number minus 1. And here, these are subscripts. So they're just saying this would be like the 4th term, the starting term. This would be a sub 4 for x to the 4th. Now 4 minus 1 is 3. So this would be a sub 3 for 4 minus 1, x to the 3. And it goes on that way. So we want to come up with a factor. How could we get that critical first factor? And then we can use that to find q of x, and then we can factor q of x. How could we do this? Well, one thing we could do is this. And this is the rational zeros theorem. So when we talk about a rational number, what we really mean are all the integers and fractions. And the reason I bring those two groups together, integers are fractions. So take an integer, -3. So -3, well, we could call that -3/1. Or we could call it -9/3. All of these are -3. So when we talk about rational numbers, we're not just talking about like 3/4 or 1/2. We're also including integers as well. Numbers you count on your fingers and numbers you count on your fingers with negative signs, in addition to the fractions. So basically, all the real numbers that aren't irrational, that's what we're talking about. And of course, we're not talking about numbers with I in it either. So rational numbers, this covers a lot of ground. Now, what this says is this: if there is some rational number that will make this, say, equal to 0, and that means it's going to be a factor, x minus that rational number will be a factor. If that's true, then this p is a factor of a sub 0. And this q is a factor of a sub n. So what we need to do is we need to find p and q, and that means we need to look at the factors of a0, and we need to look at the factors of an. In other words, we're going to look at the factors of the constant term and the factors of the lead coefficient. So let's take a look. Now, what's going to happen here is we're going to find out there's more than one factor for a0 and there's more than one factor for an. So we're going to get a list of possibilities for p and a list of possibilities for q. And since we want p over q, that means we need to consider all possible combinations of numbers from this list over numbers from that list. So we're going to generate really a whole bunch of fractions or rational numbers. So let's take a look. Let's look at an example. So let's say we have this. So now this is something we could factor using guess and check, but let's use it just to see how the rational zeros theorem works. So a sub 0 in this case is -2. A sub n, or the lead coefficient, well, this is the lead term, it has the highest power. Its coefficient is 1. Don't forget there's that invisible 1 there. So we've got this. So for p, we need to consider the factors of -2. So what numbers multiply to give us -2? And what we're going to look for in this case are integers. So let's think about this in terms of integers. What integers multiply to give us -2? Well, -1 times 2, that'll do it. Also, 1 times -2, that will also give us -2. So these are going to be sources, potential sources for p. -1, 2, or 1, or -2. One of those could be our p. Actually, multiple could be our p, but that's another story. Now, q comes from factors of an, or 1. So what numbers, what integers multiply to give us 1? Well, 1 times 1, and -1 times -1. So now we've got all the factors. Now we're going to look at the ratio. So P over Q. Well, what are the different factors that we have? Well, we have -2, -1, 1, and 2. And I'm looking at the factors up here for the possible factors of P. For possible factors of Q, we just have either +1 or -1. And so that sets up the ratio of P over Q. Now what we're going to do is this. We're going to come up with every possible combination of a P number over a Q number. And that's going to generate all the possible rational zeros. Now here's the thing. We're going to get a bunch of rational zeros here. It doesn't mean all of them work. It doesn't even mean any of them work. So what we're going to have to do is come up with these rational zeros, or potential ones, I should say. And then we're going to have to test them. We'll see if they actually work. And if they don't work, what does that say? Well, if none of our potential rational zeros work, what that means is that this polynomial has zeros that are not rational. So that's going to mean possibly irrational numbers like √2 or 3 plus √5. We've ran into numbers like this when we use the quadratic formula. Other numbers we might run into using the quadratic formula could be complex numbers like 3i, for example, or 2 minus 6i. So if the rationals don't work, then that means these roots are going to be irrational or complex. But this polynomial will have roots, and that's something we're going to see when we get to the fundamental theorem of algebra in a little bit. So this is what we've got. Let's take a look at the possibilities. So let's start with Q being -1. So look at it, -2, -1, 1 and 2 over -1. And basically we're going to divide each of these numbers by -1. So -2 divided by -1 is 2. -1 divided by -1 is 1. 1 divided by -1 is -1. 2 divided by -1 is -2. So these are possible zeros. And they didn't turn out to be fractional. They're fractions. They just have denominators of 1. Now let's consider Q as 1. So we have -2, -1, 1 and 2, all divided by 1. So again, we divide each number by 1. And what we're going to get is -2, -1, 1, and 2. And that's it. So to look at all possible rational zeros, we combine the two lists. The list when Q is -1 and when Q is 1. And we're only looking for unique numbers here. So it turns out what we end up getting if we combine these two lists into a set, really, a set of numbers we're going to test. We get -2, -1, 1, and 2. So these are the numbers we need to test. Now these are potential zeros. They don't necessarily work. So we have to test them, plug them into f of x, and see what we get. Now, for the sake of time, I'm just going to give you the results when I do this. So if we plug in -1, we're going to get -2. So that one didn't work. All right. Now let's try -1. I'm sorry. Let's try 2. We'll do 2. If we plug in 2, we get 4. And for these to work, we need to get 0. These are actually zeros of f of x. We should get 0. We're not getting 0. So bad luck so far. Let's try 1. Now f of 1 does work. We got a 0. Remember, this is the rational zeros theorem. It's the rational numbers we plug back into our f of x, or our polynomial, and it makes it equal to 0. So this means we have a factor of x, and you always do the subtraction. We're always subtracting that 0, x minus 1. And then finally, f of negative 2. Well, that also equals 0. That works. So that means x minus negative 2 or x plus 2, those are going to be our two factors. So this one worked, and that one worked. Now, what this says is this. And you can verify this, but this means f of x is going to be equal to x minus 1. X plus 2, which we can verify using the guess and check method. What two numbers add up to positive 1 but multiply to negative 2? Well, negative 1 and positive 2. So that's one way we can apply this. Let's take a look at another example. So let's say we're going to try this. Now, we need to come up with some kind of factor here. And we can try the rational zeros there. That's the one that we have. So we want to look at factors of the constant term and factors of the lead coefficient. So if we think about negative 12, so where p is going to come from, one of the factors here. What are the pairs of numbers that multiply to give you negative 12? Well, we could do negative 1 times 12. We could do 1 times negative 12. We could do negative 2 times 6. We could do 2 times 6. We could do negative 3 times 4. We could do 3 times 4. And that's it, because we'll then say, well, we could do 6 times 2, but we've already got that in here. No, let me get a negative in here. It's a negative 6. That's a negative 4. Because we want these to multiply to negative 12. So that's how we can break down P, or at least get numbers that we could use for P by breaking down that constant term. Now we need the lead coefficient for Q, and that's just a positive 1. So again, what are numbers that multiply to positive 1? Well, 1 times 1, but also negative 1 times negative 1. That will also give you positive 1. So when we consider a P over Q, we're going to get this. So the different numbers that we have here, negative 12, negative 6, negative 4, negative 3, negative 2, negative 1, 1, 2, 3, 4, 6, and 12. Squeeze in a 12 there. And then we have -1 and +1 for Q, possibilities for Q. So again, we're going to do the same thing. Let's consider, say, when Q is -1. And we're going to divide each of the numbers in the list by -1. So we'll get 12, 6, 4, 3, 2, 1, -1, -2, -3, -4, -6, and -12. So if we let Q be -1, this is what we're going to get. Now if Q's +1, well, same thing. -12, -6, -4, -3, -2, -1, 1, 2, 3, 4, 6, and 12. And dividing by 1, of course, doesn't change anything. So we're just going to get this list. So now we've got our two lists. We're going to combine them into one. And again, we're going to not worry about duplicates. We're just looking for unique numbers that appear in one list or the other. And if we look at everything, the lists are basically the same. They're going to basically boil down to this set. And that's going to be it. Now, admittedly, testing each of these, especially in a cubic equation or degree 3 equation, this could get really tedious. But sometimes those are the cards that we're dealt. Now, sort of a tip I want to share with you on this. Looking at our polynomial again. This is a degree 3. So once we find a factor of this degree 3, if we divide that factor, x minus some constant, we're going to get a degree 2 polynomial for our q of x. And so we could just apply the quadratic formula to that degree 2 polynomial, and then we don't have to keep testing these if we don't want. Once we get one factor, again, we can divide this by that factor, get q of x, and just use a quadratic formula. Now, let's say we do test these, though. So what happens? Well, it turns out that if you go -2 cubed minus 10 times -2 minus 12, -8 plus 20 minus 12, which is 0. So x equals -2. Plug it into this, it becomes 0. So that means x minus -2 or x plus 2 is a factor of that polynomial. So what I'm going to do is, instead of testing these, there's a bunch to test, I'm just going to divide this into that, because this is what we found out. because this is a factor, that means x cubed minus 10x minus 12 is equal to x plus 2 times some q of x. So if we divide both sides by x plus 2, we'll get q of x. And there we go. So to do the division, again, it's recommended, just because it's faster, to use synthetic division. Now, to use synthetic division, though, this isn't standard form, and we are missing an x squared term. So we need to put in a placeholder. So that's what we're going to do. This is the division. So to do this division using synthetic division, because this is an x plus 2, a minus 2 to start out synthetic division. Now the coefficients we don't modify. So you have 1, 0, negative 10, negative 12. Bring down the lead coefficient, and away we go. Negative 2 times 1 is negative 2. Add, we get negative 2. Negative 2 times negative 2 is positive 4. Add, we get negative 6. Negative 2 times negative 6, positive 12. We add, we get 0. That's the remainder. That's the constant. This is the coefficient for x and the coefficient for x squared. So q of x is this division. So what did q of x turn out to be? Well, what q of x turns out to be is x squared. And then we have minus 2x, because that's the coefficient for x, minus 6, and there's no remainder. Okay. So the thing we might look at here is, can we factor this? Now we know x plus 2 is one of the factors for here, for our overall polynomial, the one we started with. So we just need to factor the rest of it, which is q of x. Can we factor this? And it turns out, using the techniques that we've seen in this class or the previous class, we really can't. So we have to break out sort of the tool that always gets the job done, quadratic formula. So our a is 1, our b is negative 2, and our c is negative 6. And that's the quadratic formula. And whenever we have a quadratic, this is sort of a go-to. If we can't figure out how to factor it, and it could be factorable using techniques we've seen before, but it just might be too tricky. If you get really in a rut, and especially if you're on a test, and it's okay to use the quadratic formula, that's what it is. It lets you factor quadratics. So negative 2 plus or minus the square root, negative 2 squared, getting ahead of myself, minus 4 times 1 times negative 6. Over 2 times 1. So now we're going to simplify this. Negative negative is positive 2. We get 4. Minus times minus is going to be a plus, so this will be a plus here. Then 4 times 1 times 6 is 24 over 2. So what this becomes, and we can break this down. 28 is 4 times 7. And maybe it's been a while since you've seen this, but there's a rule that goes like this for square roots. Square root of a times b is the square root of a times the square root of b. And if a over b, it does the same thing. So what we're going to do is use that here. Now, just a little off to the side. This works for multiplication and division. Doesn't work for addition or subtraction. Just keep that in mind. But for division or multiplication, the square root will break up. So with this, to plus or minus square root 4 square root 7 over 2. Now you might ask some questions here. How come I made 28 4 times 7 instead of 2 times 14? And you're right, I could have done that, but here's the reason why. I remember that if I take the square root of 4, I get an integer. It's a nice root to get. And I'll just have to live, so to speak, with the square root of 7. It's going to be irrational. I'll just have to leave it as a symbol, square root of 7. But this will become a nice simple 2. But if I did 2 times 14, I get square root 2 times square root 14. Those are both irrational numbers, and I can't really do much with them. So because I knew I can take the square root of 4, that meant I'm going to factor this into 4 times 7. Just sort of thinking ahead to the next step. So let's do this. 2 plus or minus now 2 root 7 over 2. And again, this is that idea that comes up in algebra. A plus or minus b over c is a over c plus or minus b over c. So we could do the same thing here. Or another thing you could do, to simplify, you could factor out 2. And factor that out from the top, like a greatest common factor. Those will cancel. And you're left with this. So this means that quadratic has roots of this and this. And there we go. So what does this say? Well, what it says is this: the original polynomial this right here. This can be broken down into a product of factors. That first one, x plus 2, then x minus 1 minus root 7, and then x plus, oh sorry, x minus, sorry, they're always going to be minus, and then we might have minuses that come together as double negatives that make things positive. The plus or minus is on the inside here. So this became that. We have one rational zero and two irrational zeros. Two roots that the rational zeros theorem would not have found. So now we were asked to solve for x. So to solve for x, well, we're going to use the zero product principle. Three things multiply together. This thing times this whole thing times this whole thing. Those things multiply together give you 0. So what makes this 0? Well, when x is -2. -2 plus 2 is 0. The same thing, well, this one, not the same thing. X minus this equals 0 when? Well, when x is this. When this subtracts itself, well, anything subtracting itself is 0. Same thing here. This subtract itself is 0. So when solving for x, if this is our equation here, well, x is going to be this. Numbers in this set. And there you go. So the story here is this. We use the rational zeros theorem to come up with one zero that works. And once we have that 1, 0, we can come up with that factor, x plus 2. And then, because the original 0 was -2. We came up with our rational zeros using the theorem. We test -2. We found out -2 makes the polynomial equal 0. So x minus -2, that's where you get the plus. X minus -2 becomes x plus 2, and this becomes one of our factors. So we divide this by the factor that we found. That gave us that quadratic formula, and or that quadratic equation, and then we use a quadratic formula to find the missing zeros. And that's something we can do with the rational zeros theorem. It's not going to necessarily find all the zeros for us, and we might not want to test all those numbers, but as long as it finds 1, maybe 2, that might be enough for us to get a q of x. It's a quadratic, and then use the quadratic formula. All right. Now, as we've seen, polynomials can have rational roots, but they can also have irrational roots, like 1 minus square root 7, and they can also have complex roots. And remember, for rational zeros, roots are zeros. Not only are rational numbers fractions, they're also integers, like -3, -4, 7, and 23. But they could have irrational zeros and, for example, what we just saw, 1 plus or minus the square root of 7. We had a 1 plus square root 7 as a root and a 1 minus square root 7 as a root. or 0. So they could be irrational or complex zeros. Now, complex means they contain irrational numbers, like 2 plus 7i, something like that. So we're going to take a look at these complex zeros. We've looked at a way to come up with rational zeros using the rational zeros theorem, the ratio of p over q, where p is one of the factors of the constant term, and q is going to be one of the factors of the lead coefficient. And then for irrational numbers or irrational roots, well, we encountered those using the quadratic formula. So we need to talk about complex zeros a little bit. And there's a guideline for these. Well, it's a rule. And it goes like this. If a plus bi is a root or 0, then so is a minus bi. So if you have complex roots, they're always going to be in pairs. So if you have this, you automatically have this as a root. If you have this, you automatically have that as a root. So that's something to keep in mind with polynomials. The complex roots are going to be in pairs. So if you find one, you can automatically assume the other exists. And that gives you a free root, which is nice, or a free zero. So let's take a look. Now let's say we have this. Now it turns out, and this is just a freebie, but x minus 1 is a factor. Now what this means, let's say this is f of x. This is the same as saying that f of 1 was equal to 0. Well, let's verify that. How would you come up with that? Well, again, you want to take rational zeros theorem. So p, well, we're going to look at factors of 13, or negative 13. So what numbers multiply to give you negative 13? And again, we're multiplying integers in this case. So, well, negative 1 times 13, and then 1 times negative 13. All right, well, there we go. And then for q, well, the lead coefficient is 1. So numbers that multiply to 1. Well, 1 times 1, and negative 1 times negative 1. So let's take a look at our p over q. We could have negative 13, negative 1, 1, and 13. Those are possible values of p. Possible values of q will be negative 1 and 1. So if we look at, say, q being negative 1, so we divide each of the numbers in the numerator by negative 1. Well, we get 13, 1, -1, and -13. And then for Q is 1, we have -13, -1, 1, and 13. And that just gives us -13, -1, 1, and 13. So these are the ratios, P over Q. There's our P numbers over the Q, P numbers over that Q, because Q could be -1 or +1. What we get are numbers we can test. And so combining these two together and looking at the unique numbers, we've got -13, -1, 1, and 13. And it turns out, if you test these numbers, the only one that's going to make this equal to 0 sure enough. And sure enough, that's the only one that gives you, well, that's the one that gives you 0. Now, maybe there's others though. Maybe we should check. Just want to show you that this is the only one that works. Because let's say we didn't know that. Because again, that was some knowledge we had at the beginning of the problem. So let's make sure these others aren't also going to give us zeros. So we do know now that 1 works. We'll keep that one. So what about -1? Now this will be squared, so it just becomes regular +1. So +1 times 5, this is still going to be that minus sign stays and nothing gets modified here because you get 5 times +1 and the minus is going to stay. But this one becomes -17, -13. Not even close. -36 did not give us 0. So -1 didn't work. Now for this one, let me grab a calculator real quick. Let's see. Because you're going to do 13 cubed. So that's going to come out to, let's see, so we're going to test this one here. F of 13, let's see, it's 2197, or 13 cubed, minus 5 times 13 squared, plus 17 times 13 minus 13. So 2197 minus, let's see, 13 squared times 5, 845, plus, and 17 times 13, 221, minus 13, and then combining these, what do we get here? Doesn't look like it's going to be 0. Sure enough, it isn't. which is 1560, but it's not 0. So 13 doesn't work. So far, only 1 has worked, which is what we had in the beginning. But let's just, for the sake of doing it, let's test negative 13. Maybe my clue here was an oversight and I missed some rational number. Well, let's find out. So f of negative 13. So this will be negative 2197. And then we'll have negative, is that 221? Oh, 845. 845. And this is another positive times negative, because this will get squared, so this will become positive times a negative, so we end up getting a negative. Another positive and a negative. Ah, there's your 221. Minus 13. Let's see, this doesn't look like 0 at all. Nope, we're even more off. Minus 3276. So sure enough, we tried all the zeros, or all the candidates for 0, and only one of them worked. So sure enough, our initial hint was correct. Well, let's go with that. So what does that mean? Well, what it means is that we figured out one factor. And of course, the way we do our factors, x minus that 0, or x minus 1, is our factor. So that means we're going to divide this into this to get our q of x. So what this is saying is that f of x is x minus 1 times q of x. For the find q of x, we'll divide this into this. Or in other words, divide this into this, what f of x is. Now we're going to use synthetic division. It just makes things faster. So keep the coefficients. One times 1 is 1. Add them, you get negative 4. 1 times negative 4 is negative 4. Add them, we get 13. 1 times 13 is 13. Add them, we get 0. That's the remainder, constant term, x coefficient, x squared coefficient. So q of x, what we need to factor is what's going to be that. Now, if you try guess and check, you're not going to get anywhere with this one. We better use the quadratic formula. So our a is 1, b is negative 4, and c is 13. 2. All right. So we've got that. Now I'm going to take a quick break and let's review, or let's return to what we were doing originally. We were originally going to look at this idea that complex roots show up in pairs. So what we've got is a square root of a negative number. When we get the square root of a negative number, that means this is going to become complex. And with the plus and minus, we're going to get 2 answers. So sure enough, we're going to get some complex roots that are in pairs. Let's keep going. So the negative factors out as an I. Square root of 36 is 6 over 2. And you could divide the 2 into each of these or factor out a 2. But what you'll get is 2 plus or minus 3, and customarily we actually put the I on that side. So 2 went in the 6 3 times, 2 goes in the 4 2 times, the I just remains. And sure enough, what's going to happen, we're going to get 2 roots. The plus version, and then the minus version. A plus BI, A minus BI. So what does this say? Well, we use the rational zeros theorem to figure out or to verify that 1 was a root or a 0 of our polynomial. In other words, it meant that x minus 1 is a factor. And then same thing here. That means x minus this, x minus this, well, that gives us a breakdown of our polynomial. And you might say, well, why come we're always subtracting these zeros or these roots? And the reason is, if 1 is a root, that means f of 1 has to be 0. So that means if we put in 1 here, we better get 0. So if we plug in 1 here, well, it's really not going to matter. We'll get some funny stuff here. We'll get something. Maybe not funny, but we'll get something. But then we'll get 1 minus 1 is 0, which zeroes out everything. And so by having 1 minus 1, that's why we set it up this way. So we were ready to receive that 1 so we can zero out and then zero out everything else. All right. So this leads us up to the fundamental theorem of algebra. And basically what it says is this: all polynomials have roots. All polynomials have at least one complex root. Now, this root could be repeated. So that is a possibility. Now, let's see. Now, something to mention, and there's a little caveat to this. if we count repeated roots, in other words, if we put the roots in a list, for example, like if the root's repeated 3 times, we list that root 3 times. Let's say we do something like that. So counting repeated roots the number of times they are repeated and counting other roots we get in roots if n is the degree of the polynomial So what it's saying is this. If you have a polynomial of degree n, you will have n roots. Now, some of those roots might be just repeats of the same number, but you're going to have n roots no matter what. So let's say you could get a situation, say, like this. Now, we saw this earlier, that this factored out to this. And so we have 3 unique roots. So this has a degree 3. It's a 3rd degree polynomial. And it had 3 roots. So it had 3 unique roots. Now, another possibility could be something like this. Let's say we take a look at this. Well, what this is x minus 1 cubed, or x minus 1, x minus 1, x minus 1. So in this case, we have 3 factors of x minus 1, and each one is made 0 when x is 1. So there's 1 0. One way you can think of it, there's a unique number that makes this thing 0, and it's 1. Now you could say this. You could say for the roots, they're 1, 1, and 1. So 3 ones would be your 3 roots. Or you'll see it like this. The root singular is 1 repeated 3 times. Either way you think of it as 3 roots of 1 or 1 repeated 3 times, here's the thing. These 3 factors have to be there to multiply to give you that. And so this is the idea of the fundamental theorem of algebra, and with that little caveat added to it. every polynomial will have at least one root that could be repeated. Or another way of saying it, it'll have as many roots as the degree on that polynomial. And then you're going to get these factors. Another way of thinking of it, the number of factors of a polynomial will equal the degree of the polynomial, whether these factors are repeated or not. All the factors together. Degree 3 polynomial, you need 3 factors, whether they're the same or not. And that's the idea of the fundamental theorem of algebra. So this leads us to the linear factorization theorem. If that's true, and if we know the roots of a polynomial, then maybe we could assemble that polynomial starting with roots. So we have this. Linear factorization theorem. So what it says is this. Now let's go back. Let's recall that our basic form is an xn plus an minus 1 xn minus 1 something like this. Well, what we're going to say is this. If Cn minus 1, C1 are roots of f of x, and where some C sub k's, this is just a generic subscript is what it is. I know these are pretty generic, but this is an even more generic one. You could say where some of these C's in here, that might be a better way of thinking of it. Some of these in here are repeated in the list. So what we mean is, for example, that last example we saw where we had that cubic function that had the 3 1s as roots. So there could be like a 1, a 1, a 1, and then a 2, 7 plus 3i, 7 minus 3i. But we're going to take repeated roots and actually repeat them the number of times they are in fact repeated. We'll repeat them in that list. So you have like 1, 1, 1, comma, 2, 2 plus 3i, 2 minus 3i, something like that. All right. So we're going to rewrite f of x. So if we know the roots of f of x, we can rewrite f of x like this. We can write it as a product of these factors made from those roots. And then we put on the tag on the front of it, a sub n. So let's do an example. Let's see how this works. So we want to construct a degree 3 polynomial using roots 1 and 5i and the fact that f of negative 1 equals 104, negative 104. Well, we have a degree 3, so that means we need 3 factors. So that means we need 3 roots, whether those roots are repeated or not. We only have 2 roots given, so what can we do? Well, we want to recall that complex numbers always show up in pairs. Now, in this case, what complex number do we have? Well, we're given 5i. But 5i is technically 0 plus 5i. A plus bi. The real part is 0. The imaginary part is 5. So we have 0 plus 5i. That means we're going to have a negative 1. 0 minus 5i, or just 5i and negative 5i. So there's our third root. And here we're using that fact that complex numbers show up in pairs to get that second root. So whatever f of x is, it's going to be a sub n, x minus a root, x minus a root, and then negative 5i, x minus negative 5i, minus a negative, that's a double negative, that's positive, plus 5i. So we can combine these. X squared plus 5ix minus 5ix minus 25i squared. I know it might be hard to see, but that's a minus 25i, and that's a square, so it's I squared. X squared plus 5ix minus 5ix, those cancel. So that's going to be, they'll go away, leaving minus 25. And then I squared, that's negative 1. So let's squeeze that square in there a little bit better. It's a little more visible, but that's an I squared. And what we're going to end up doing is, well, I squared is negative 1. So we get an x minus 1, x squared, negative times negative is plus 25. And then finally, we just need to multiply these two binomials. And we could FOIL these again. An x cubed plus 25x minus x squared minus 25. Or f of x is a sub n x cubed minus x squared plus 25x minus 25. So it looks like we've got it almost figured out. We just need to find an, and that's where we use the fact that f of minus 1 is minus 104. So that means minus 104 is a sub n times minus 1 cubed minus 1 squared plus 25 times minus 1 minus 25. Minus 1, subtract 1, because minus 1 squared is just 1. That subtraction is still there, so you subtract positive 1. Minus 25, minus 25. And when you do the addition here, what you'll get minus 52. Divide both sides by minus 52, you'll get 2 equals a sub n. So that means f of x is 2 x cubed minus x squared plus 25x minus 25. And we distribute that 2 through. And that's going to be your answer. All right. So we do need that little bit of information. The f of -1 equals -104. That lets us find a sub n and complete the polynomial. So the last thing to mention in this section is Descartes' rule of signs. And this kind of helps us, perhaps before we jump into the rational zeros theorem, how many rational zeros might we expect? Because the rational zeros theorem, technically none of them have to work. We can come up with some candidate rational zeros. We could test all of them, and none of them will work. Is there maybe a little better guidance? Is how certain can we be that we have real roots? Now, these real roots could be irrational. They don't have to be rational. But are we certain that we get real roots? Now, that's going to be important because, well, with real roots, if we think about what these functions do, what a root is, we have a function. A root or a zero is where our function crosses the x-axis. And if we don't have any real roots, well, that means it's not equal to 0 with any real numbers. When we try to solve f of x equals 0, that gives us the zeros or the roots. Say this is our f of x. If there are no real numbers that make this equal to 0, that means there are no places on the x-axis where this function crosses the x-axis. So it could be doing something like this. And it never crosses the x-axis. Now, it is, say this is a polynomial, so it does have roots. Well, not roots, zeros is what I should say, or maybe roots is the best way to put it, but they're going to be complex. They're going to be complex. So zeros are roots, that's fine. But they're going to be complex. That means it's complex numbers, not numbers on the real number line that is the x-axis. So it does have roots, it has zeros, but they're not going to be any numbers on the x-axis. That means this thing doesn't cross the x-axis. So how do we know when it does that? To make sure. Well, that's where Descartes' rule of signs can help us out. And this one has a lot of pieces to it, but what we're going to look for is how many real zeros, real numbers, numbers on the x-axis, are going to be zeros for this polynomial. And here are the guidelines. For the number of positive real roots, the number of positive real roots. How many of those could we expect? And this isn't going to be very exact. We're just going to have options, really. So it's going to be this, either the same as the number of sign changes of f of x. So the number of positive real roots could be the number of sign changes in f of x. What does that mean, sign changes? Well, what we're looking for is this. Let's say f of x, it's equal to this. So here we start out with a positive term, then we go to a negative term, and then we go to a positive term. So that means there are 2 sign changes. We went from positive to negative. So that's a change. And then we went from negative to positive. So that means we have 2 sign changes. So what this is saying is that the number of positive real roots will be equal to the number of sign changes. All right. Well, that's part of it. So that would seem there's going to be 2 positive real roots here. Well, it's a little more complicated. Here's the second part. That's one possible number of positive real roots. So we could have 2 here. Now let's see. The other option is the number of sign changes minus some even number. So let's go back to our example here. X squared minus 6x plus 2. Positive the negative, negative the positive, those are 2 sign changes. So from the first part, we learned that we could possibly have 2 positive real roots for this polynomial. Well, that's great. But this says kind of an or. You take the number of sign changes, which we found out to be, in this case, 2, and if you subtract some even number, that could also give you the number of sign changes. I'm not sign changes, I'm sorry, positive real roots. So we could have, by the first rule, 2 positive real roots. But then by this new second rule, we can have 2 minus an even number of positive real roots. Now, we're talking about even number. We're actually talking about positive even numbers, not like -2 or -4. We're talking about like 2, 4, 6, 8, these kinds of things. Well, we're not going to have a negative number of something. We're not going to have a negative number of positive real roots. So this here, it's got to be some kind of positive number. So the number of real roots could be 2, which we found out from that first rule, or it's 2 minus some even number. What even number can we subtract without getting some negative result? Well, that's 2. So we could have 2 minus 2 is 0 positive real roots. So from these first 2 rules, we're not going to have totally exact answers here. We could find out we have 2 positive real roots for this polynomial, or we could have 0 positive real roots for that polynomial. All right. So far, the number of positive real roots well, for this polynomial, I'll put it up here so we don't forget. It could be 0 or 2. Now I want to talk about the subtracting of the even number business. This could get a little confusing. So let's say we had this. Let's say there were 8 sign changes. So this could be like a really big polynomial where we have a positive term, then a negative term, to a positive term, to a negative term. In this, we have 8 changes in sign. So by the first rule, we could potentially have 8 positive real roots. Or by the second rule, so we could have this, 8 positive reals. Or by the second rule, we could have this. We could have 8 minus 2 is 6. 8 minus 4 is 4. And 8 minus 6 is 2. In addition to this one. So with these two rules, as long as we could have 8 possible reals if there's 8 sign changes. We could do that. Or other options, in addition to this one, the sign changes minus an even number, sign changes minus an even number, sign changes minus an even number. As long as we can always subtract an even number, oh, better not forget, we could have 0. As long as we could subtract an even number and not get a negative result, those are also possibilities for the number of positive reals that we could have for that polynomial. So using these two rules, what we find out is this. If we have 8 sign changes, we could have 8 positive reals, because that's the number of sign changes, or we could have 6 positive reals, or we could have 4 positive reals, or 2 positive reals, or 0 positive reals. So that's how that subtracting of an even number works. So in our case, we could have 2 because it equals the number of sign changes, or 2 minus 2 is 0, so we could have 0 positive reals. There's one more rule. Now this one is more concrete. One sign change means 1 positive real. So this one we do have something we can bank on. So if we have something, say, like this, no sign change, because we went from positive to positive, but then we went from positive to negative. This says there's at least one positive real root, and we can count on it. And so now whether that real root is irrational, or it could be rational, where we could find out what it is using the rational zeros theorem, don't know. But this tells us there's at least one positive real root. All right, so that's the first half of Descartes' rule of signs. Second half. We talked about the number of positive reals. Now it's time for the number of negative reals. So this is very similar to the first one. It's the number of sign changes and you might say, well, you can't say f of x because the number of sign changes for f of x was the number of positive reals, unless the number of positives always equals the number of negatives. Not the case with real roots. Now, don't confuse that with the complex roots, where whenever there's an a plus bi, there's an a minus bi. We don't have something like that for real roots. But it's the number of sign changes of f of negative x. So think negative x, negative roots. Or, well, here, let me do an example. Let's say we have f of x is negative x squared minus x minus 2. This has no sign changes in it. So that means there are no positive roots in this case. So, but let's look at f of negative x. Now this says there are going to be some negative roots. There's one sign change and a second sign change. We got two sign changes here. So that means there are possibly two negative roots for this, because f of negative x has two sign changes. I'm going to write this one up here just so we don't forget it. The other possibility, and again, it's that second rule, it's going to be similar. The number of sign changes in f of minus x minus an even number. The number of sign changes in f of minus x minus an even number. So again, taking a look at this, f of minus x was negative x squared plus x minus 2. So we had two sign changes. So from our first part, that means there are two negative real roots. But we can also subtract an even number from 2 and still get something that isn't negative. We could also have 2 minus 2 equals 0 negative reals. That's also a possibility. So this has 0 or 2 negative reals. Now this is interesting because if we look at f of x, before we put in negative x, there's no sign changes. So that means there are no positive roots. This is a degree 2. So that means it has to have at least 2 roots or one root that's repeated twice. That's the fundamental theorem of algebra. So basically this is what we've got. This has either 2 negative real roots, there are no positives, or it doesn't have any negative reals also. That would mean the only option left for roots would be complex. This would have complex roots. If it has 0 negatives, and since there's no sign changes for f of x, there's 0 sign changes, that means it has 0 positive roots. Well, if there's 0 negatives and 0 positives, that means that the only roots would be complex. But it could have 2 negative real roots, though. That's another possibility. And with 2 negative real roots for a degree 2 polynomial, that would mean it would have no complex roots. Anyway, finally, we have this something concrete. If f, or a little more concrete, if f of negative x has one sign change, then it has one negative root. So the number of positive roots, the number of negative roots, it's the same kind of idea. We count the number of sign changes, and that gives us one possibility for the number of roots. Then we consider all the possible combinations of subtracting that number of, taking that number of sign changes and subtracting even numbers until we get 0. And all those subtractions, the results of those, that tells us other possible numbers of either positive roots or negative. And then finally, if there's one sign change, we're guaranteed at least one positive or negative root, or one positive root, or possibly one negative root. When we're looking at sign changes for positive roots, we look at f of x. When we're looking at the number of sign changes for negative roots, we look at f of negative x. All right. So a couple examples. So let's take a look at f of x here. So we're looking at positives. Now in this one, there's one sign change. From positive to negative terms. So that means there's one positive real. And that's that one that we can bank on. That's going to be true. And if you try to say, well, what's an one subtract an even number? Well, you get a negative result. We don't worry about those. All right. So for negative reals, well, we need to look at f of negative x. And in this one, we get one sign change. Positive, positive, and then the negative. So one sign change. So that means one negative real. So we're guaranteed that positive real. Because remember, you get that one sign change, that's guaranteed. If there's only one sign change in the entire polynomial, you're good to go. So we've completely assured ourselves there's one positive real and there's one negative real. Now these are two different roots, and degree 2 polynomial, so we found all the roots. Well, we can at least we have an idea that one of them's a positive real, one's a negative real. Now just to check, this we can factor. So we're going to get f of x, and it just so happens this factors to x minus 2, x plus 1. If we set that equal to 0, well, what makes this 0? Well, x being positive 2, x being negative 1. All right, so let's look at another example. So let's take a look at positive reals. Well, sign changes. Well, just looking at f of x, negative to positive, so that's 1, then back to negative, and then back to positive, that's 3. So there's 3 sign changes. Also, we could have 3 minus an even number, which is 1. So this tells us one possible number of positive real roots. Another possibility is 3 minus 2, it's an even number, is equal to 1. And this is the only even number we could subtract from 3 to not let it become negative. That subtraction to become negative. So this basically says this. There are 3 or 1 positive real root. So we could have 3 positive real roots, and for a degree 3 polynomial, that would mean all the roots are positive reals. Or we could have 1 positive real, and the other 2, maybe they're negative, or maybe they're complex. So let's take a look at negatives. F of negative x. This will come out to 2x cubed. Well, here, I'll put it in. Cubing a negative keeps it negative. So we'll get 2, so negative and that negative be positive. Negative x cubed is negative x cubed. Negative x with a 3. And so negative times negative would give you a positive. Plus x squared. Negative negative is a positive, and plus 7. And if we take a look at this, there's no sign change. That means 0 negative reals. So where does this leave us? Well, we've got this. We could have 3 or 1 positives, and we know we have 0 negatives. So forget negative real roots. We could have 3 positive real roots or 1 positive real root. Well, 3 positive real roots, well, I mean, degree 3 polynomial, all the roots are positive reals. Could this ever possibly be the answer, though? Yes, it could be. The reason is, if we have 1 positive real root, that means since we have 0 negative reals, those remaining 2 roots are going to be complex. So you'd have 1 positive real and 2 possibly complex reals. And here's the thing about complex. They're in pairs. There could be an a plus bi and an a minus bi that are roots in addition to some positive real root. So we have basically 2 scenarios. Three positive real roots or 1 positive real root and 2 complex roots, a plus bi and a minus bi. So we could have 3 positive real roots or 1 positive real root and then 2 complex roots, a plus bi, a minus bi. And that gives us some insight possibly to what could be going on here. All right, well, that's it for this section. If you have any questions, let me know. Other than that, have a wonderful evening.